The temperature dropped to negative 28 degrees. The wind was cutting sideways through the trees. Snow was piling up fast, and Liam, a 69-year-old retired engineer, standing alone deep in the Alaskan wilderness, had made a decision that every survival expert around him said was flat out wrong. He wasn't building a log cabin. He wasn't digging an earthen shelter. He wasn't following any of the survival manuals stacked on his shelf back home. He was building something the U.S. Navy invented in 1941, a curved metal shell. And he was nestling it into the root system of a tree so ancient it had already outlived 3 generations of his family. His neighbors thought he'd lost his mind. His son called twice trying to talk him out of it. One local builder told him that metal in an Alaskan winter was basically a refrigerator with a door. And maybe they were right. The temperature dropped to negative 28 degrees. The wind was cutting sideways through the trees. Snow was piling up fast. And Liam, a 69-year-old retired engineer, standing alone deep in the Alaskan wilderness, had made a decision that every survival expert around him said was flat out wrong. He wasn't building a log cabin. He wasn't digging an earthen shelter. He wasn't following any of the survival manuals stacked on his shelf back home. He was building something the U.S. Navy invented in 1941, a curved metal shell, and he was nestling it into the root system of a tree so ancient it already outlived 3 generations of his family. His neighbors thought he'd lost his mind. His son called twice tried to talk him out of it. One local builder told him that metal in an Alaskan winter was basically a refrigerator with a door. And maybe they were right. Or maybe, after 40 years of engineering, after building structures on 4 continents, after studying cold climate physics in ways most people never think about, maybe Liam knew something they didn't. On the night of his first real temperature test, with a thermometer outside, reading negative 28 degrees Fahrenheit, Liam checked the gauge inside his finished cabin. 65 degrees. Not 65 degrees warmer than outside. 65 degrees Fahrenheit inside, sustained through the entire night, burning less than 1.5 loads of wood. That's when everything changed. Most people who want to build off-grid in Alaska start by thinking about size. How many square feet do I need? How thick should my logs be? How do I source enough timber? Liam started by asking a completely different question. He asked, where does heat actually go? It's a question that sounds simple, but the answer is what separates a man who barely survives his first winter from a man who builds a structure that outperforms everything around it by 65 degrees. Heat doesn't just leak through walls. It escapes in layers. It's stolen by wind pressing against flat surfaces. It disappears through the roof into the cold open sky. It bleeds through the floor into frozen ground. It drains through every gap, every seam, every metal fastener that creates a direct bridge between warm interior and frozen exterior. The conventional log cabin, as beautiful and traditional as it is, fights heat loss with mass. Thick logs, heavy walls, brute force. Liam decided to fight heat loss with shape, with science, with geometry. And the shape he chose was one of the most thermally efficient structures ever designed by human hands. The Quonset hut was born out of desperation. In 1941, the United States Navy needed a building that could be shipped in pieces to any corner of the world, assembled by men with no construction training in under a day, and survive conditions that would destroy conventional structures. The answer was a semicircular arch made from corrugated galvanized steel. Over 150,000 of them were built during World War II. They survived Pacific typhoons. They stood up to Arctic cold in Alaska and the Aleutian Islands. Soldiers lived in them, worked in them, stored ammunition in them. When the war ended, thousands of them were repurposed into homes, churches, and community centers across rural America. Then the world moved on. New materials, new designs, new homes with drywall and forced air heat. And most people forgot why the arch worked so well. Liam never forgot. The arch shape has no flat surface for wind to push against. Think about that for a moment. When 30-mile-per-hour winds hit a flat cabin wall, all that force and all that convective heat stripping hits at full impact. The wind literally tears warmth away from the surface. Meteorologists call it wind chill. Builders call it a problem they solve by making walls thicker. The arch solves it differently. Wind hits the curve and slides over. Force and friction both reduce dramatically. The structure doesn't fight the wind. It deflects it. But that's only the beginning. Inside a curved structure, warm air doesn't pool uselessly at the peak the way it does in a square room. The curve deflects rising heat back downward along the walls, naturally circulating warmth through the living space without fans or ductwork. You feel that heat. It doesn't float 12 feet above your head. And the surface area to volume ratio of a semicircle is significantly lower than any rectangular structure with the same floor space. Less surface area means less total area through which heat can escape. Every geometric decision in the design works in your favor. This is what Liam understood that his neighbors didn't. The metal shell wasn't the insulator. The shape itself was doing critical thermal work before a single piece of insulation was installed. Now here's where most builders, even experienced ones, make the mistake that costs them everything. They see corrugated galvanized steel, and they think cold. They think metal conducts temperature. They think about touching a car door handle on a January morning, and they cannot imagine living inside something like that. They're thinking about it wrong. The steel shell is not the insulator. It is the outer weather barrier. Its job is to stop wind, rain, snow, and moisture from ever reaching the insulation system behind it. That is all, and it does that job perfectly. The insulation lives on the inside of the shell, and what Liam built was not a single insulation layer. It was a 4-layer thermal fortress that produced a wall assembly of approximately R55. For context, most building codes in Alaska require R38. Liam built walls that were 40% above code, in a structure most people assumed would be colder than a standard cabin. The first layer went directly onto the corrugated metal interior. Closed-cell spray polyurethane foam, applied at 4 inches thick. This material has an R value of 6 to 7 per inch. For inches gives you R, 24 to R, 28 in that first layer alone. But the R value is almost secondary. The more critical function of closed-cell spray foam in a metal structure is complete air sealing. Every corrugated gap, every bolt penetration, every seam where panels join. The foam fills all of it. Cold air infiltration, which is responsible for an enormous percentage of heat loss in any structure, is eliminated entirely, and the foam bonds to the metal, adding measurable structural rigidity that increases snow load resistance. The second layer was 2-inch polyisosanurate rigid board insulation installed over the cured spray foam. Polyiso performs at approximately R 13 per inch, giving R 26 from this layer alone. It was adhered with construction adhesive. No metal fasteners. This was a deliberate choice Liam made from his engineering background. Any metal fastener penetrating from interior to exterior creates what engineers call a thermal bridge, a direct conductive path through which heat travels from warm to cold. 1 steel screw per square foot sound harmless. Multiply it by hundreds of fasteners, and you have measurable, significant heat loss. Adhesive eliminates that entirely. Combined, those 2 layers produce insulation in the R 50 to R 54 range. The third layer was a 6 mil polyethylene vapor barrier running continuously from floor to peak, with every seam taped using acoustic sealant tape. In extreme cold climates, moisture migration is one of the most dangerous and misunderstood threats to insulation performance. Warm, humid interior air will always try to move toward cold, dry exterior air. When that moisture vapor travels outward through insulation and hits a cold enough surface, it freezes. Over 1 winter, the damage is subtle. Over 5 winters, frozen moisture inside your insulation has destroyed half its R value, and you don't even know it's happening. The vapor barrier stops that migration before it starts. The fourth layer was tongue-and-groove pine paneling on interior furring strips. Pine adds roughly R 1.25 per inch of thickness. More important is its thermal mass. Wood absorbs heat slowly and releases heat slowly, buffering temperature swings throughout the day and night. Fire dies down at 2 a.m. in a poorly insulated space. You wake up cold. In a high-mass, well-insulated space, the walls themselves have been slowly releasing stored warmth for hours. You wake up comfortable. Liam also knew from decades of experience that humans in wood-paneled spaces consistently perceive the temperature as warmer, independent of actual air temperature, and tend to be comfortable at lower thermostat settings. The psychology of warmth is a real, measurable phenomenon. Total wall assembly, R 55, but Liam had not chosen his location by accident, and the location was doing work that no insulation can replicate. The site sat where an ancient tree, a tree with a trunk wider than most living rooms, had fallen years before, its massive root system thrusting upward from the earth and creating a natural wall 8 feet tall on the north and west sides of the build site. The trunk itself ran along the back of the structure. Every engineer and every survivalist who has studied cold climate building understands one thing above all else. Wind is a true enemy. At negative 20 degrees Fahrenheit with no wind, the cold is serious, survivable, manageable. At negative 20 degrees Fahrenheit with a 30-mile-per-hour wind, the effective temperature on exposed surfaces and on the exterior of any building drops to negative 60. That is not a difference of degree. That is a difference of survival. The root wall and fallen trunk block prevailing wind on 2 full sides of the structure, not partially, completely. That single factor alone accounts for a reduction in convective heat loss of up to 40% on those wall faces. But the tree was doing more than blocking wind. Ancient dense hardwood holds thermal energy with surprising persistence. The trunk had absorbed heat during daylight hours through solar radiation. As night temperatures plunged, that stored energy was radiating slowly outward against the exterior of the cabin wall, adding a passive heat source that requires no fuel and no maintenance. The root system had created a natural earthen berm along the lower section of the structure's exterior. A berm is packed earth pressing against the wall. Soil has modest R value on its own, approximately R 0.25 per inch. But 24 inches of compacted earth gives R 6 on that section of wall. More critically, it eliminates wind exposure on the berm's surface entirely, reduces temperature differential, and anchors the lower structure against frost heaving, a phenomenon where freezing soil expands and shifts building foundations over time. The forest canopy directly overhead provided a factor that almost no builder accounts for: protection from sky radiation cooling. Clear open sky at night acts as a heat sink. Exposed surfaces, including rooftops, radiate their heat upward into the cold sky at a rate that can reduce effective exterior temperature by several additional degrees. Dense tree canopy overhead blocks that radiation exchange the same way a blanket blocks convective cooling from your body. Before Liam installed a single bolt on his Quonset frame, the site itself was already functioning as a passive thermal system. Inside the finished cabin, every heating decision was made with the same engineering precision. A large wood stove would have been a mistake. In a space insulated to R 55, a large stove creates an oven. The stove doesn't need to generate tremendous heat. It needs to replace the heat that minimally escapes. Liam used a small catalytic wood stove, a stove designed to burn fuel at high efficiency over a long time rather than produce rapid, intense heat. Around the base of the stove, he packed dense river stones, not for decoration. River stone is one of nature's most effective thermal mass materials. It absorbs heat rapidly during active burning and releases that heat slowly for 6 to 10 hours after the fire dies down. A well-loaded fire before sleep means stones radiating warmth into the cabin air through the entire night without any additional fuel or attention. In a survival scenario, that matters enormously. Men have died of hypothermia in their own shelters because they woke at 3 a.m. to find the fire had gone out and the temperature had crashed. The thermal mass system eliminates that risk. The floor was another critical decision. Cold floors are responsible for a disproportionate share of perceived cold indoors. The human body loses heat through conduction with cold surfaces at a rate far faster than through cold air alone. Liam elevated the subfloor on pressure-treated timber framing with 2 inches of polyiso rigid foam between framing and subfloor deck. Wool rugs covered the finished floor surface. Wool is one of the most effective natural insulators at floor level and traps a layer of still warm air between its fibers. Perceived interior temperature in a space with properly insulated warm floors is measurably 5 to 8 degrees higher than a space with the same air temperature and cold floors. Fresh air intake was handled with a simple but ingenious passive system. A coiled copper pipe was buried 18 inches underground and ran from outside to inside. At that depth in Alaskan soil, the ground temperature stays near 40 degrees Fahrenheit year-round, because the earth below the frost line is thermally stable regardless of surface conditions. Outside air at negative 30 degrees enters the buried pipe, travels through the coil, and arrives inside the cabin pre-warmed to near 40 degrees. The difference between negative 30 air and 40-degree air entering your breathing space is the difference between a cold draft that strips heat from a room and ventilation that barely affects interior temperature at all. No electricity, no moving parts, physics doing the work. When Liam ran his temperature comparison on a night when outside air sat at negative 28 degrees Fahrenheit, a traditional log cabin of comparable size in the region was recording internal temperatures of 32 degrees with its wood stove burning 6 full loads of wood over 8 hours to hold that. Liam's Quonset hideout recorded 65 degrees Fahrenheit, sustained, through the entire night, on 1.5 loads of wood. Let that land. The traditional log cabin, the structure every manual recommends, the shelter that has been used in Alaska for over a century, needed 4 times the fuel to achieve half the warmth. In comfortable conditions, that's an efficiency win. In a survival scenario, in a storm that locks you inside for 5 days, in a situation where you have a limited wood supply, in a medical emergency where you cannot go outside to cut more fuel, that difference is not comfort. That is life and death. 1.5 loads of wood for an entire night at negative 20 outside. That is a structure that gives you options. That is a structure that gives you margin. For anyone who wants to build this themselves, the sequence matters as much as the materials. Start with site selection. A flat open clearing is the worst possible choice in cold climates. Look for natural windbreaks, fallen trees, rock outcroppings, hillsides, dense forest edges. Face your door south or southeast to capture the low winter sun angles that are your best free heat source. Don't fight the landscape. Read it. Foundation choices depend on permanence. For a semi-permanent structure, pressure-treated timber skids on compacted gravel work well, and allow the structure to be relocated. For permanent insulation in Alaska, helical piers driven below frost depth are far superior to concrete pours, which are difficult to execute correctly in cold weather and vulnerable to frost heave if improperly installed. Quonset frame assembly is straightforward. Preformed steel arch panels bolt together in sequence. A 16-foot wide by 20-foot long structure, which gives you 320 square feet of livable space, can be assembled by 2 people in 1 to 2 days. The simplicity of the assembly is one of the system's great advantages over conventional framing. Apply spray foam immediately after the shell is complete. Do not wait. In wet climates and cold environments, moisture can infiltrate bare corrugated steel panels within hours, and any moisture trapped beneath insulation will cause long-term degradation. Foam the entire interior in one continuous session if possible. Cut and fit rigid foam board over cured spray foam using construction adhesive only. No fasteners. Be meticulous about fitting around every penetration and in every curved section near the spring line where arch meets floor. Run vapor barrier continuously from floor to peak with all seams sealed. Use a proper acoustic sealant tape, not standard plastic tape, which loses adhesion in cold conditions. Install interior wood furring strips over the vapor barrier to create a fastening surface for paneling. Furring strips also create a small air gap that adds marginal additional R value and allows any incidental moisture to drain rather than accumulate. Run your stovepipe through the end wall, not through the roof. Roof penetrations in heavy snow environments are persistent leak risks. End wall penetrations are easier to seal, easier to inspect, and easier to repair. Finally, berm. Excavate around the structure and pack the soil against exterior walls up to the spring line of the arch compacted firmly in layers. Plant native ground cover over the berm surface to stabilize it against erosion over time. A mature berm with established roots will hold its position indefinitely. What Liam built in that forest wasn't just a cabin. He is 69 years old. He spent 4 decades solving complex structural problems on projects most engineers never see. And when it came time to build a thing he would trust with his own life in the harshest environment on the continent, he didn't reach for a conventional answer. He went back to first principles. He asked what shape does the physics favor? He asked where does heat actually go. He asked how can the land itself do the work that fuel would otherwise have to do. And the answer he built returned 65 degrees of warmth on a night when the world outside was trying to kill everything in it. There is a lesson in that which goes well beyond cabins and insulation. The people who survive extreme conditions, the people who genuinely thrive in environments where others merely endure, are almost never the ones with the most brute force. They're the ones who understand what they're working against. They're the ones who align themselves with forces that are already operating. The arch of physics, the mass of ancient wood, the stable warmth buried 18 inches underground. Rather than spending all their energy fighting those forces head-on, Liam didn't fight the Alaskan winter. He understood it. He planned for it. He built a structure that took the best ideas from military engineers who had already solved this problem 80 years ago, layered modern insulation science on top of those ideas, and then sat in a forest and read the land until he found a location where nature herself was already doing half the work. 1.5 loads of wood. 65 degrees. If you've been dreaming about an off-grid structure, a hunting retreat, a survival hideout, a homestead shelter that will genuinely protect you, stop thinking about how big you can build. Start thinking about how smart you can build. The wilderness doesn't grade on effort. It grades on results. And Liam passed.